Welcome to episode 29 of the Eyes on Privacy podcast. This month I'm joined by Keith Watson and Josh Gillum. I'm Preston Wiley, and today we're going to talk about basically something that's been in the security news, and Josh is going to introduce the topic this month.
Today we're going to talk about the Diffie-Hellman protocol weakness to it, which is going to affect everything from HTTPS, SSH, VPN, and this shows how it can be mitigated, thankfully, either on the browser side or on the server side, and both. So now we go and talk into some of the issues of just where the weakness becomes in the protocol. I don't know if Keith wants to start with where the weakness is in the protocol, how you can do the degradation to 512-bit encryption.
Sure, we can talk a little bit about that. So the Logjam Attack really works on flaws in the TLS protocol, and it basically allows a man-in-the-middle attack to downgrade these TLS connections all the way down to what we call export-grade crypto, which is, in the case of Diffie-Hellman, would be about 512-bit key exchange. And so basically this allows the attacker to basically read the connection and possibly modify data in the exchange. And so by doing that, the attacker's inserting themselves in the middle of that communication. And so if you go back to what we talked about with the freak attack, that was also taking advantage of export-grade ciphers in the TLS protocol, so the SSL protocol, where those protocols were still sitting around, and the server, or the man in the middle, would basically say, no, I don't want that. I want something. What's the lowest set of bits you got? And basically, by downgrading that to the lowest cipher suite with the least number of bits, it increased the likelihood that the attacker could factor some keys involved in the key exchange. So this is very similar to that process. And so there's a set of ciphers for Diffie-Hellman known as the DHE export ciphers, and these affect pretty much a large number of modern browsers. Even the current versions of Firefox and Chrome are affected by this problem. And so in addition, this is something that affects servers as well. And so on either side of the connection, if this flaw exists, the man in the middle could take advantage of it. And so this is a fairly serious problem. The way to correct it, which has been proposed, is to kind of make sure that both sides, the server and the client, won't accept these lower number of bits for the key exchange. And so we haven't seen that yet. Chrome is still vulnerable. Firefox is still vulnerable in a lot of cases. It appears that Internet Explorer works okay. Surprising. But so that's this particular problem.
Well, just a comment on that, and essentially how Diffie-Hellman works, and why people may think, well, this is an encrypted thing, so how can somebody do a man-in-the-middle attack? Well, Diffie-Hellman is a key exchange protocol that essentially allows two machines to kind of agree on a key that they will use to encrypt communications with each other, and the Diffie-Hellman involved here uses essentially prime numbers that both machines know what the prime numbers are, and the prime numbers aren't necessarily a secret. The secrets are kind of are just a math algorithm that's done by each, that kind of based on those primes and the things they choose, that they can kind of reverse the equations done and figure out what each other's secrets are, based on numbers that they have chosen themselves. But the problem is that essentially a man in the middle can inject a new prime number into the mix, since it can kind of read the communication and alter it, and that is essentially the flaw in the protocol. So basically, it takes the unencrypted prime number and changes it. to something that is of export grade, or 200 or 512 bits, that is easier to kind of break. That's essentially the flaw.
Yep.
And it seems currently that 8.4% of the top million domains were currently vulnerable, so not a huge amount of numbers, percentage-wise, but still a goodly amount out there. Almost a tenth of it.
A couple million sites, nothing big.
I actually think we talked about export grade encryption like a podcast or two ago, and why did it exist? What
I think that was our
what's the
last
history of it? Yeah, it might have been the last one. I'm not sure, but we actually talked about that, and the kind of the talking about this flaw again. The flaw is this flaw exists even if export grade encryption or DH export is disabled, because the protocol doesn't check, doesn't have a way to basically say, oh, this is DHE, not DHE export. It's kind of something that doesn't exist in the protocol itself to determine what DH bit size is being used. So the fix that was proposed, and I think is being used by some, is to check the size of that prime number to make sure it meets the tolerance. Essentially, is at least 768 bits. I think is the fix.
I think they said the 768 would be an academic team could possibly break, but in a nation state could possibly still break the 1024.
Right. Yeah, because it requires exponentially greater computing power to get those higher bit numbers. So that brings up kind of the second point of this. We talked a little bit about the flaw in the TLS protocol itself. There's also a flaw in the key exchange, which Preston talked about, and really that affects not just websites and web browsers, but also SSH and VPNs, because they do the same sort of key exchange through Diffie-Hellman that's needed in order to figure out what symmetric key is going to be used for the bulk encryption and decryption of data sent over a connection. And so this problem with Diffie-Hellman applies to these other protocols as well. And that's where we talk about a little bit of the nation-state actor with enough computing resources to compute a lot of the primes that are used in these key exchanges. The other aspect of it is a lot of these softwares, such as Apache and SSH, shipped with a bunch of default primes in their configuration files, their prime groups. And most administrators didn't, and really there's not been a lot of documentation saying, oh yeah, you should go and recompute your prime number groups. And so they didn't. So they're using the default ones. And so that also simplifies a big part of the attack here as well.
Right, and I don't think that was necessarily considered a problem, because the primes, as I mentioned before, are in the case of Exchange are a public, a known thing. It was the math that was the complicated part. Knowing the primes wasn't something that wouldn't really assist you in doing in figuring out the key. But as computing resources have gotten better, and this the paper that's linked on the website that we will be posting talks about basically the way that you can do a lot of the computing on these prime numbers in advance and basically store it, and then you just have to do a little bit of computation when you actually see a prime number to actually figure out what the secrets are. So they essentially have a method to do a lot of the computing in advance, and for 512-bit, it's fairly trivial, really, on like an Amazon web services or a decent cluster of computers. I think they used an idle time type system where they are essentially using the idle times of a bunch of computers to compute things. And using that, they were able to attack, including the FBI. Apparently, the FBI was vulnerable to the attack. Apparently, they aren't now, but they were at the time. So that was interesting.
Another aspect to the conspiracy theory nuts would be the NSA, as part of the Snowden leaks. There was a discussion of a project that talked about VPN decryption infrastructure, and basically that the IKE protocol, which is the key exchange protocol in IPsec and used in a lot of VPNs, it was actually highlighted in one of the slides that they presented. And so the theory is that the NSA perhaps knew about this weakness in Diffie-Hellman key exchange and has been taking advantage of it too. So take that for what it's worth. I don't know if it's true, but you're looking at the classified material here, it may be. And so I think this highlights an issue going on right now with a lot of cryptographic protocols and libraries, and that is increased scrutiny, which is a good thing. I mean, yeah, we're finding a lot of flaws that exist everywhere, and those have to be fixed, but the fact that we're looking and the fact that we're finding and fixing is a good thing. Part of this will help us learn for the future, so we'll know not to do certain things certain ways, but it's that increased scrutiny that will help secure a lot of these systems that are weak today, and hopefully this will raise the bar in terms of compromising these systems and protocols once we get a little more eyeballs looking at it.
And we continue to see the issues, the 20-year-old problem that keeps cropping up with the export grade encryption that was put in there back in the 90s, and it seems to keep cropping up, and we are seeing why it was a bad idea to essentially do things like that. So a lot of this was done in the name of backward compatibility as well, which you wonder, like, well, backward compatibility isn't necessarily always a good thing, and I think we're starting to figure that out too. That people need to be, you need to be up to date. You need to, you should be using the latest versions of, especially software that can lead to a lot of security issues. I mean, Chrome is automatically updating. Firefox will automatically update. Internet Explorer is getting fairly good about automatically updating. So, that didn't used to be the case. So we're I think the backward compatibility thing is starting to not fly as much as it used to.
I think we are, as an industry, updating software a little more quickly. I wouldn't say we're doing it at the enterprise level as quickly as I would like, honestly, but I think the vendors are certainly putting in some effort into providing updates a little more quickly and trying to fix some problems more quickly than they have in the past. There's always the corner cases. I think Apple's got a couple outstanding bugs that everybody knows about that they're not fixing, but Microsoft has done that before. Even Chrome has done that before. So we're getting better. We're not there yet, but I think we are getting better overall.
So my somewhat impression of this attack, or flaw or vulnerability or whatever you want to call it, as far as what they call logjam, is it's not as bad as a lot of the other ones we've seen. In a lot of ways, because it requires it still requires, even with the 512 bit, it still requires a lot of effort on the part of the attacker to pull off, even with the small bits, just the small key, the export level key. It still requires a lot of effort to accomplish, which I guess speaks pretty well, I guess, of Diffie-Hellman in general, that even at with export grade level, it still requires a lot of work to break. We're not talking, and if you used, and I'm sure if you used, if you didn't use pre-computed primes, even at the 512-bit level, you'd be a lot safer than what you are now. Apparently, Apache. I think there was something in this article about Apache shipping with one prime hard coded into the code for the export grade. So.
And one
So,
thing
yeah.
one thing we should point out, and it's true, is if you look at the title of the academic paper, it says how Diffie-Hellman fails in practice. And it's not that Diffie-Hellman as a key exchange protocol is flawed. It's that the way we've implemented it and the way we've put it into practice, that's where the problem is. The fact that we have these export grade ciphers, the fact that we have these pre-computed groups that nobody changes, that leads to weaknesses, but not in the weakness of Diffie-Hellman, but because of reuse, of having weak keys that we know are weak, and making that something that somebody can take advantage of. That's where the real problem is. It's not that the math is wrong, because it's not. It's that we have implemented stuff poorly, which is typically true in crypto. You've got developers developing their own crypto system. Yeah, don't do that.
Yes, if you read this paper, you'd be surprised, I think, by the number of just shortcuts essentially that were taken for computing resources purposes, not necessarily out of malice or anything like that, but just to conserve computing resources. Like I think there's an example of one of the things that uses Diffie-Hellman essentially using the same secret every time they do it, because the other side doesn't. It's they use the same secret until you essentially restart. I mean, that seems bad.
Yeah.
That seems like a bad
secrets.
thing.
Yeah, reusing secrets generally not always a good thing.
So I mean, but that's that maybe in a router scenario or a low device that doesn't have a whole lot of computing power, you can't necessarily recompute these primes. You have to use a pre-computed, and you have to a lot of CPU resources need to be saved, because these algorithms aren't necessarily cheap, and this prime generation and things like that is expensive.
Yep.
So, and then we definitely should talk about the recommendations that they made in this paper.
Absolutely.
So,
Josh, you want to talk about those?
Well, I think for some of the recommendations, it was disable the export cipher suites on the server side. If you can deploy elliptic curve Diffie-Hellman, make sure you generate a strong, unique grouping, or would those be the primes in the grouping?
yes.
Yes.
Yeah.
So that's on the server side, right?
Yep.
So what else can we do?
On the browser side, block it or have it check the bit length if it's less than 1024 to just not accept it.
So that really requires us to make sure we're updated on our browsers once they fix the problem, right?
Right, because
which we're not there yet, because we know that there are still problems.
Yeah, mine's still vulnerable at 38.0 for Firefox.
So that's one other thing. The website, if you go to it, will actually show you a little banner at the top of the page indicating whether your browser is vulnerable to the problem or not.
Yep, and the website is weakdh.org.
Yep. So, a couple things for us to do. Hopefully we'll get some fixes for our browsers soon, but you can solve the server problem today.
Yeah, and we're going to. I mean, on the when this is posted, and I posted it with the invite. There's a website, weekdh.org, and they have a guide to deploying Diffie-Hellman for TLS, and it has a lot of mitigation techniques for the various web servers that you would potentially be using to essentially get elliptic curve Diffie-Hellman enabled and used by default on the servers, and also doing pre-computed or not using pre-computed Diffie-Hellman parameters, because if the thing you're talking to doesn't support elliptic curve Diffie-Hellman, then it will downgrade to not using elliptic curve Diffie-Hellman. So you still would potentially have an issue with the using pre-computed primes. And it mentions a lot of different technologies that would use it. Probably the more common ones. So I definitely think the recommendations on the deploying guide are probably in order of easy to hard, or things you definitely should do, to things that are probably just a good idea. The first one is disable export cipher suites. I think that's just a good idea. You should definitely do that without question, because
there's no point to it anymore.
Export cipher suites are pretty much universally not secure anymore. I mean, we're talking about 20 years worth of time for the computing resources to meet up with the ability to crack these things. And the next one is deploying elliptic curve Diffie-Hellman, which is a good idea, definitely a good idea. But as I said, it's not necessarily always going to be used. So the third one is generate a strong, unique Diffie-Hellman group. So essentially computing your own primes. And that is still, I was looking at that, and it's still not, essentially using your own unique Diffie-Hellman group is not necessarily supported by everything out there either. So that's not necessarily something you're going to be able to do. But if you're using the 1024 grouping, the only people that would potentially have the computing resources to crack that are nation states, and the paper mentions that based on the Edward Snowden revelations, that might have occurred, but we don't know that.
Alrighty, I think we've covered it.
Yeah, I think so too. And the paper is interesting. It's it's an academic paper, so those can be a little bit hard to read. But I think this one is more readable than some of the other ones I've read, to be honest. So I would, if you're interested, I'd recommend reading it, or at least reading the beginning of it. So and skipping down to the last part on recommendations as well. So we'll post that the website in the when we post this this video. And anything else to add?
Nothing.
We covered it.
All right. Well, thanks to Josh Gillum and Keith Watson. I'm Preston Wiley, and keep your eyes on privacy.